Well, so today our speaker is Eli Shamovich from Ben-Gurion University, and the title of his talk is Localizations of Algebras of Noncommutative Functions. Please.
Thank you very much, Alexei, for inviting me and giving me this opportunity. So just a warning ahead of time. When I agreed to give this talk, I was hoping that the entire mess in the Middle East will be over by that point of time. It's not. So if there is a warning of an impending missile attack, then I'm gonna go and hide and maybe take you with me. But yeah, so I hope it won't happen this period of time. Okay, so I would like to tell you a bit about, because the seminar is called Algebras and Analysis, and I feel that this topic is particularly relevant. It's about like an analytic objects, but we do some algebraic constructions with them. So we localize them now because everything is going to be non-commutative in this setting. The localization is going to be a bit tricky. So that's what I'm going to talk about. And this is joint work with Meric Augat from James Madison and Rob Martin from Manitoba. So feel free to stop me at any point of time and ask questions. Otherwise, I can go blabbering on and on. So let's start with the kind of motivation for what I'm going to talk about. So we have the polynomial ring. Okay, so the polynomial ring has a lot of nice properties. Kind of one of the first rings students meet. It is a principal ideal domain, and it has the Euclidean algorithm, which is super nice. And it has a field of fractions, which is just the rational function. So here it's all well known and documented. Now, if we fix some positive number r, we can define the ring of analytic functions. Mostly I will talk about entire functions, so r is going to be infinity. I'm going to allow that as well. I don't mind letting r be infinity. But yeah, so we have the ring of analytic functions on a disk of radius r. That thing is a topological ring. It is not quite a PID anymore, but it is true that the ideals are either singly generated or infinitely generated. And that's the reason is that it is a Bezout ring. Now, the Euclidean algorithm implies the Bezout identity, but there are rings which have the Bezout identity without having the Euclidean algorithm, and this is one of them. And it also has a nice ring of fractions because everything is commutative here, and it's in the domain, and this is the ring of meromorphic functions, the disk. Okay, so what do I want to do with that? So my goal is to talk about non-commutative functions, which I'll just for brevity, I'll write NC. And the basic object is the free algebra. Okay, even in this setting, it's already quite not trivial to construct rational functions, because apparently once you kind of, for example, when I teach complex analysis, then the first example of an analytic function is a polynomial, the second one is a rational function. Now here, polynomials are quite easy. So we just take the free algebra, the universal algebra on degenerators, and it has some nice properties which are analogous in some sense to the previous iteration, which is for d equals 1, which is the polynomial ring. So, so P.M. Cohn, whose work is influential in what I'm going to talk about, observed that this thing is a free ideal ring. So that means that if you take any left or right ideal inside the free algebra, it's a free module over the algebra. It's free as a module over the algebra. And it has something called the weak algorithm, which will not be very relevant, but it is, it's kind of a generalization of the Euclidean algorithm to the non-commutative setting. And this is basically how Cohn proves that this is a free ideal ring. But what's going to be here instead of the rational functions? Well, that's not entirely clear, and let me tell you about this. So the definition, which will be important for our talk today is that the ring R is called the semi-free ideal ring, like I told you what a free ideal ring is. And for me, mostly the semi-free will be important because this is the analog of a semi-free ideal ring in the commutative setting is a Bezout domain. If every finitely generated right ideal is free as a module. Okay? Now, these objects exist, they're not, but they're, as you see, they're very special. Now, the notion is left-right symmetric. Unlike the free ideal ring, in the case of the free algebra, the free ideal ring property is preserved both by right and left ideals. In general, it might be only true for right ideals or only for left ideals. But the semi-free ideal ring is true for both left and right ideals. Okay, so for me, a semi-free ideal ring is again a ring where every finitely generated ideal is free as a module. Okay, and the theorem of Cohn tells us that every semi-fair, so every semi-free ideal ring, has a unique universal skew field of fractions. Now, a skew field of fractions, skew field is the old version of division ring. I'm going to use Cohn's terminology, so I'm going to talk about skew fields. But that means that basically it's a ring where every element which is not zero is invertible on both sides. So that's a skew field for me. And universal in the sense here of universality is a bit trickier than in the classical setting. So in the commutative setting, if you take just the ring of if you have a domain and you take its field of fractions, then if you have a map, injective map from your domain into any other field, then there is a map from the field of fractions. That's not quite what happens in the non-commutative setting. It's a bit subtler. We need to talk about epic morphisms and so on, but it has a universal property, which I'm going to swipe under the rug because it's not going to be crucial idea. And how does he construct it? So this construction, I feel, is kind of relevant to us in analysis, especially people dealing with operator algebras or more operator spaces or more generally matrix normed spaces. So the construction goes like this. You take your ring R, and you define what an inner rank is. So you take every matrix in your ring, and you say that the inner rank of the matrix is the minimal integer such that you can factor A as a B times C, where this integer P is the number of columns and rows of B and C respectively. Okay. Of course, this minimum is at most N, because you can always write A as A times identity, right? So this is at most N, but it might be strictly less. And we say that A is full if the inner rank is N. Otherwise, it's non-full. And we do this for all matrices of all sizes over R. So we can do. And if R is a semisphere, it turns out, and more generally, something called the Sylvester domain, which is a generalization of this notion, then the set of all non-full matrices, so basically matrices that factor as a tall matrix times a long matrix, is something called a prime matrix ideal by Cohn. So this is kind of an ideal like structure which captures the localization property in classically. So what classically happens is that if you have a domain, the complement of zero is a prime ideal. So you localize at the complement of zero, right? And here what happens is that you need all the matrices of all sizes over R. You take the non-full ones which behave like zero, because these shouldn't be invertible over every skew field because you can factor them. And then you construct the universal skew field of fractions by basically inverting all full matrices. Okay. And that is kind of, it feels to me at least, coming from the analytic side, as very natural, because, well, if you want to capture non-commutativity somehow, you want to capture it in matrices over your object. So, and that's what Cohn basically does. Okay. But however, the problem is that, okay, so we said that the free algebra is a free ideal ring, so it's particular, it has this universal skew field of fractions, but I mean, being an analyst, so I can always view my polynomials as functions in some sense. I can always evaluate them on tuples of matrices or tuples of operators. What can I do for this weird object called the universal skew field of fractions that Cohn constructs? So there is a slightly different construction that I would like to discuss now. And that construction, so usually this universal free skew field is denoted like this, with this weird kind of the free algebra brackets combined with the skew field brackets. And for this, I'm going to present everything as functions. So I'm going to set this MD to be the basically the finite dimensional representation space of the free algebra. So these are D tuples of n by n matrices of all sizes over C, because I will only work over C here. The construction of Cohn, of course, works for arbitrary fields, but that's not important for me here. And now this is kind of going to be my analog of my affine space. So polynomials definitely can be defined as functions on this space. Just evaluate this D tuple the polynomial, and you get some matrix. We'll see the properties of these functions in a few slides. So now what do you do? How do you build your skew field kind of naively? Okay, what you want to do is you want to invert things in your skew field. So you write all possible finite rational expressions in elements of your skew field, of the free algebra. So you get various expressions like this here, or that here, or the sum, or the inverse of the commutator, or even zero inverse. I don't mind. Okay. Just everything. I just write whatever I want, but just finitely many inverses and algebraic combinations. Okay. And I define for every such rational expression its domain. The domain is going to be the set of all D tuples of matrices where this makes sense. So I can plug in this matrix into this expression, and the expression basically compiles. So every inverse, everything that's written in an inverse is invertible. So for example, the domain of this expression is obviously empty. There is nothing here. However, for this guy, the inverse of the commutator, you look at the first level. So if you look at just by scalar, just 1 by 1 matrices, of course, the domain is empty. But for 2 by 2, there are plenty of matrices where it's defined. So the domain is not empty. And of course, if you are not empty on a level, then you shouldn't be empty on multiples of this level, because you can just take a direct sum, right? And because everything can be encoded by finitely many determinants, the complement of the domain, if it's not empty, is just an algebraic variety. Okay. So I'll say that R is good if the domain is not empty. If basically what I'm saying is that if I wrote an expression which doesn't evaluate to anything on matrices, I don't like it. Okay, I will throw it away. And we're going to define an equivalence relation. So saying that R1 and R2 are good. I'm going to define an equivalence relation if for all x on in the intersection of their domains, they're equal. So this is kind of an analytic extension kind of relation, right? One expression is defined on a certain set, another expression is defined on another set, and on the intersection, they should agree to define the same function. Okay. Thing is, why would these expressions, their domains, why would they intersect? As I've mentioned previously, on levels high enough, if your domain is not empty, it's just a complement of an algebraic variety. So it's a big open set. and such sets, that Zariski dense sets, they intersect. Okay, and since if you have something on the level, say 2 for one of them and something on level 7 for another, then on level 14 you'll have both of them, and there they will intersect already. Okay, and then for me, a non-commutative rational function is the equivalence class of these good expressions. And the theorem of Amitsur, and the way I present it is a theorem of Kaluzhny, Verbovetsky, and Vinnikov, that this construction actually gives you the free skew fields. You can actually view them as functions on this non-commutative space MD, like rational functions. So what Amitsur proved is actually something about certain types of skew fields, and Dima and Victor actually proved that if you take the ultra product of all kind of certain skew fields you get from matrices, basically, not from matrices themselves, but somehow something called generic matrices. If you take the ultra product, this is a good field in the sense of Amitsur, so that is already enough to find. Okay. But of course, again, this construction is a bit more hands-on because there are already some rational expressions and not inverting matrices, but rather polynomials. And but still, this relation is kind of hard to understand. So I'm going to say a bit more about this. So if I have a non-commutative rational function, I'm going to say that its domain is just the union of the domains of the relation of the good expressions they represented. Okay. That's basically where I can extend this rational function to. Now, if 0 is in the domain of f, you can also do things if it's not, but let me keep to that simple setting, and usually it's enough for most things that I'm doing. And you can write something called the realization for this function. So you can simplify this complicated expression to something that contains one inverse. But since nothing in life is free, you have to pay a price. And the price is that you invert no longer just polynomials, but matrices of polynomials again. But basically what it says that there exists some matrices in Mn and some vectors Bc and Cn, such that I can define this as the expression, such that whenever f is defined, I can write this essentially, provided I choose the minimal n possible. You can construct this basically for polynomials. It's not very hard to construct such matrices, and then you kind of write out what you have to do for inversion, which is basically like a Schur complement, and for products and so on, and you see how you get everything. The most interesting thing is that the domain of f is precisely where the determinant of this pencil that I have here is non-zero, where I evaluate using tensor products. Okay. Now, what happens is that so basically it tells me that at least if 0 is in my domain, I have a concrete way to write my function as just with a single inverse, like we would expect from a rational function. The problem is, of course, that the inverse is of a linear pencil rather than a single. Sorry, I think it should be here. Okay. Rather than just taking, so this is called the realization of f. There are other types of realizations in literature, but that one I'm going to use throughout the talk. There's something called the FM realization, other realizations, but that's kind of the one I want to use. So these are rational functions. So this is a complicated object, but now we at least have some handle on it, and we can study it, and somehow a lot of this theory translates to pencils, and it recently became important, for example, in computer science and other things which are completely applied, and I don't think either Amitsur or Cohn or anybody had an idea of these kind of applications of this. Well, not quite, but I'm not going to go into this. Okay, so what is the application? What was the main motivation for us to study these objects? Well, one of the main motivations. So this is a famous theorem of Hagerup and Torbjorn's. It is something which became rather popular in recent years. That's called strong approximation. And it says the following thing. So I'm going to formulate it the way Hagerup and Torbjornson do, or did actually. But modern day people in group theory are very much interested in that, and they have slightly different formulations. But the gist of things is the following thing. You take a probability space, and you take a sequence x1 to xd n of n by n self-adjoint random matrices which are independently distributed with Gaussian entries and some assumption about the mean and the variance of these matrices. This is just normalization in some sense. So basically, you assume also that the entries are independent. So since they're self-adjoint on the diagonal, you just have real entries, and off diagonally you have, of course, these should be dependent because this is one is an adjoint of the other. But for each one above the diagonal, the real and the imaginary part are also independent and distributed with corresponding mean and variance. That's the idea. Okay, so you have these matrices. So basically, you can kind of take random growing matrices distributed with accordance to this law. And what they prove in a very complicated paper in the Annals, that there exists some null subset of omega, such that for all points outside of it, and every polynomial in the free algebra, if you increase the sizes and you take the norm of this polynomial evaluated on your random variables at these points, these converge to certain operators, the free semicirculars, the polynomial in the free norm of the polynomial in the free semicircular variable. This greatly strengthens the result of Voiculescu, which proved it for kind of some sense convergence and expectation in traces of these things. But that's much stronger. Okay? So basically, in some sense, the way people in free probability formulate this claim is that you can evaluate, you can understand polynomials in these complicated operators using these random matrices. Let me define what these free, so this give an example of what this, I'm not going to define them, I'm just going to give an example of these free semicirculars, and because I'm going to need the setup anyway in the future. So I'm going to denote by, let me just, this will be really visible because of the zoom. Is that okay?
Oh, yes, yes. Mm-hmm.
So for every D, I'm going to define the full Fox space, which is just the Hilbert space direct sum of CD tensor n with itself, where the convention is that the 0th tensor power is just C. Okay. This is going to be some Hilbert space called the full Fox space. It comes from physics in some sense. Don't ask me about the physical meaning of this. But the way I like to see it is kind of analogous to the classical H2 on the disk. The classical H2 on the disk is just the closure of the polynomial ring with respect to the inner product, which makes the monomials orthonormal. Same here. Take the free algebra, you define an inner product that makes the monomials orthonormal, and you take the completion. That's your Hilbert space, and that's the full Fock space. And the full Fock space has some nice operators in it. This is the left shifts. What they do is just they multiply on the left by the ith variable. Okay, just like the shift on the Hardy space on the disk. And H infinity D, I'm just going to say this is the word closed algebra generated by the left shift, the unit of word closed algebra generated by the left shift. And the name H infinity comes from the analogy again from H infinity of the disk. Because this algebra, if you take the shift on H2 and you look at this algebra, the word closed algebra generated by one and the shift, you get precisely the bounded analytic functions on the disk. And this is also true in this setting. This is actually quite fruitful setting for a lot of non-commutative version of function theory, because a lot of things that are true for H2 are also true in this setting. Somehow, this space, in spite of it being much more complicated, it's better behaved than any commutative space. Definitely better behaved than H2 on the polydisk, definitely better behaved than H2 on the ball. And it's still better behaved even than something called the Drury-Arveson space on the ball. But my semicirculars, for example, you can define them abstractly as certain types of self-adjoint operate, but you can take just twice the real part of these left shifts. This is going to be the semicircular operators, free semicircular. So you can, if you never saw the free semicirculars before this talk, you can think about these guys. Okay. So why is it nice, this construction of free skew fields? Because actually, if you take an element of the free skew field, it makes sense to evaluate it on every stably finite algebra. This is a result of Cohn and Held and Mayen Speicher that used it for various free probability applications. The idea is that, so stably finite means that, so first, directly finite means that if your element is left invertible, then it's also right invertible. Okay, nothing weird happens like something in B of H and the shift. There are no things like isometries, for example. And stably finite means that it's true also for matrices. So every matrix of every size, square matrix, of course, over your algebra is invertible on the left, if and only if it's invertible on the right. And in that sense, if you take any rational function, what the problem can be? So you have this rational expression that you can write. You can ask whether its evaluation makes sense in an algebra. However, if you recall, these were equivalence related. This was an equivalence class of such expressions. And maybe different expressions in the same class give you different results. The theorem actually says that this is not the case. Okay, that this if you have a stably finite algebra, then evaluation at tuples, as long as it makes sense, respects this equivalence relation of kind of analytic continuity. Example of stably finite algebra is every tracial C-star algebra or von Neumann algebra, like the kind of the Lichen free probability. And that allowed Enoch to extend the result of Hagerup and Tourbillon to rational functions, non-commutative rational functions. So assume I take some f here such that I can evaluate it on some tuple of free semicirculars. Okay, say my free semicirculars from the previous slide. Then, for the same n like before, for n big enough, this tuple belongs to the domain of f. This must happen. And the norms still converge. So you can extend this result to rational functions, as long as the free semicircles are in the domain of f. And because the free semicircles, at least those that I've defined, generate tracial von Neumann algebra, this algebra is stably finite. So this evaluation makes sense. And there are other constructions of the free skew field using only these operators in some sense. Okay, so far for the background. Now I'm gonna shift gears into what we did. So if you have any questions, feel free to ask. Okay. So operator realizations. If you recall, there was this realization that we wrote for rational functions. So we started first by asking, what happens if we use operators instead of matrices? And of course, because usually taking a d-tuple of operators can lead to various weird phenomena, we said, okay, maybe what happens if they're compact? Okay. And the interesting thing is that, well, first of all, you can write this as long as the inverse makes sense. It gives you some kind of function, right? It does make sense to do that. And we also started to think, okay, fine, when does it make sense? Well, let's say that if we take this d-tuple of very small, let's say some kind of chosen operator and space norm, and so very small norm, say the sum of ai star ai is small. Okay. The column norm in some sense is small. Then for at least a small row norm of zi, this expression will always make sense and will be invertible. So you will have something defined on an object on well, something which behaves like an open ball in our MD, right? And it will even work for operators. So this kind of realization really looks like something defined at zero. Of course, at zero it makes sense. Okay, that's why I'm going to consider.
I'm sorry, your little f here is again sort of rational,
No,
non-commutative.
I'm not assuming rational, right? For rational, these had to be matrices, right? And I'm saying, okay, let me try and do something slightly different. I'll just define a function f like this. This
You
is a
had the
good question.
definition. Okay.
Yeah, that's just
Okay.
going to say, okay, I'm going to do the naive thing and I'm going to replace matrices with operators. Okay.
Okay. Thank you.
Good. So that's why we looked at power series. So non-commutative power series, you can guess what it is. So you just write, essentially, depends on how you like it, just write formal infinite sums over the free algebra instead of finite, or the completion of the free algebra with the adic topology with respect to the augmentation idea, or whatever you want. But you get this kind of expression. And Gelo-Popescu defined a radius of convergence for these power series. So basically, it looks like the Hadamard, the Cauchy-Hadamard formula, but instead of taking the absolute value of the coefficients, you take this kind of norm, okay, which is kind of the norm of the homogeneous component in some sense. Okay, really, it is the norm of the homogeneous component because of this. If we take this square root, this is the norm of the homogeneous component in the Fock space. Okay, and you take the limit as you take these ratios, and you get this RF, and that's going to be my definition for the radius of convergence for this function. You can do it differently, but that's all I'm going to need for today's talk. And I'm going to say that this function is entire, non-commutative entire function if this radius of convergence is infinite. Okay, and I'm going to denote by OD the ring of all NC entire functions. It's not very hard to check, and I'm going to define the non-commutative row ball in a second, that this function this series converges uniformly and absolutely on all rows of operators of row norm less than this RF, like strictly less than this. Like you fix some R less than RF, and then this power series will converge uniformly on this ball. Okay, and for such functions, you can write a realization. So what we did was, it's not a very hard theorem, but it's kind of surprising and new, even in some sense, in one variable. At least we couldn't find any direct reference to that. Is that you have an entire function if and only if this f has a minimal realization. In what sense is it minimal? I'm going to say in a second. With compact operators such that their spectral radius, this formula defined by Popescu, is 0. Okay, this is what we call quasi-nilpotent. So for one operator, this is precisely to say that you have a realization with a compact quasi-nilpotent operator. Now, what is minimal? So minimal means that if you take your A's, right, we call that the realization is basically F. I'm going to write it with kind of the variables. So I'm going to do this like this. It's going to be C star I minus some Zi AI inverse B, okay? Where C and B are some vectors in H. So minimal means that the space spanned by AI, let's say A alpha B, where alpha is a word, is dense in H. And similarly for the stars and the C. So A star alpha C, the span of these words in A applied to C is also H, okay? But here is a crucial difference between rational functions and operator realizations. So for a rational function, the minimal realization is unique up to similarity. Basically, the only thing you can do is to change A's by just apply a similarity with an invertible matrix and change C and B accordingly, so that nothing is going to change. Here it's not true, especially for operator realizations. You can have various operator realizations with they cannot be even similar. And the reason is precisely this, because we have an infinite dimensional space, density is not such a strong condition, right? We can have various densely defined weird operators mapping one to another. And in our paper, we have an example of function of one variable which has two realizations, both minimal, one compact and quasi-nilpotent, meaning it's entire. The other is the backward shift for A, right? So this is definitely not compact, definitely not quasi-nilpotent, right? So this is a bit more subtle. However, if you stick to compact operators, this minimality is sufficiently strong to guarantee a lot of things, like the domain of this rational function and so on. Okay. And therefore, we kind of stands to reason to look at this kind of local ring, right? It's not hard to prove that this is a local ring. And we define this OD0 with K here to stand for compact operators, the set of all NC functions that have a compact realization. So you can write basically whatever you can write with a compact realization like that. Okay. Now, if you have a compact realization, then if you look at this condition here, I don't know, maybe like this, you can always make it minimal and you won't change its compactness because you can compress basically to this space spanned by B, and then the resulting thing you can compress to the space spanned by C, by this thing in C, and you will get a minimal realization. This is a standard procedure in realization theory, which comes from systems and various applied things. So if you have a compact realization, you have a minimal compact realization. So this is the ring of functions defined on neighborhood of zero. So it's kind of a local ring. And you can check that it's really a local ring. It's a subring of the formal power series. And because of its natural properties, you can apply a theorem of Cohn that tells you that this thing is a semisphere. And in fact, therefore, you have a universal skew field of fractions. And these functions, just like before, just like in the case of rational functions, these functions are evaluation equivalence classes. You can say, okay, if these two functions, you can define them as kind of rational expressions in things in this ring, which agree once you evaluate them on matrix points in my space. Okay, so in some sense, you can view them as meromorphic functions because they're global, right? Having this compact realization means that, okay, maybe just like for rational functions, you might not be defined on certain finite number of levels of matrices, but then once you are defined, okay, you are gonna be defined almost everywhere. And that's because of this compact realization, because still the singularity locus of this pencil is an analytic subvariety. Okay, and that's kind of behaves a lot like a global object. Okay, this is a global meromorphic object. That's why when we wrote this paper, we called them noncommutative meromorphic functions. Okay. So as I said, these are global objects, and actually they also have compact realizations in some sense around matrix points. This is a theory developed by the rational case. Well, the rational case, you can kind of do several things. You can either pay a price by replacing the identity that I had in the pencil by not necessarily invertible operator, some other a naught. Alternatively, you can do this kind of realizations which look a lot alike with identities, but now you pay the price of A being maps. Okay. This was done by Porat and Vinnikov, and Rob with his students extended this to compact realizations for these kind of meromorphic functions. You can play the same game with other, not necessarily compacts, but Schatten von Neumann classes like trace class, Hilbert-Schmidt, and you will get some kind of semifers of non-commutative functions which have their own localizations. And the semifers are kind of, this is an idea of, if, for example, for entire functions, if you look at something which has a quasi-nilpotent realization in the trace class or in other Schatten von Neumann class, means that it has a certain growth condition in the classical sense of complex analysis, even in one variable. Okay, but somehow I want to talk a bit more about NC functions because this is somewhat still not very satisfactory, I feel, because this is a local object in some sense, this ring. I want global objects. Let me define this, what I promised to define. This is the row ball. This is the analog of the disk around the origin, the non-commutative setting for me. This is the set of all strict row contractions of matrices. And sometimes we throw in the infinite level, so strict row contractions on operators as well. And I'm going to call a function NC if it satisfies the following properties that are definitely satisfied by polynomials. If you take a tuple of matrices and you evaluate a polynomial on it, like an element of the free algebra, you get a matrix of the same size. I call this graded. Okay. Now you can define what direct sums are. So just take coordinate-wise block diagonal matrices. And of course, if you evaluate a polynomial on this thing, it's the same as evaluating on each of the components and taking the direct sum. Okay. And that should be true for my functions. And it respects similarity. So on each level, I have action by the GLN of this level, which is this action, right? I just take similarity on each coordinate. And if you have a polynomial, evaluating a polynomial on such an expression is just like evaluating a polynomial on X and taking the similarity afterwards. Okay. And I want all of these conditions to be satisfied. In fact, the interesting thing is that if you have such a function, say on the ball, and it is locally bounded, even on each level, so each point has a neighborhood where this is bounded, this function is automatically analytic, level-wise. Okay? And of course, what I'm going to say is that you can define the bounded functions, on the bounded NC functions on this ball. And this is going to be the functions which are NC, so satisfying these three properties, such that they are uniformly bounded for all X in the row ball. Okay. And that's definitely true, for example, for polynomials, because for polynomials, okay, so since everything in this ball is must-have coordinates that are contractions, so you can plug it into any polynomial, it's going to be bounded. You just bound everything by just naively with the triangle inequality. The interesting thing that if you look at the right-hand side, this is kind of a very strange object, but this is completely isometrically isomorphic to this algebra H infinity D, which I defined previously, the word-closed algebra generated by the left shifts. This is due to Popescu. My Fock space can also be viewed as functions. They're just basically now an analog of H2. This is the space of those power series with square summable Taylor coefficients, just like H2 is. And so they define also NC functions because they converge uniformly on every subball. So you have this kind of property automatically. And now an interesting result that we have just recently obtained with Rob and Meric is that if you take a function, we had previously this result with Rob and Mike Jury for rational functions. In the Fock space, which also has compact realization, then actually it extends to a slightly bigger ball. Okay, so basically, if you take a meromorphic function on C, which is also in H2 on the disk, it must have its poles some distance away from the boundary. That's precisely what happens in the non-commutative setting. And the tools going into proving this is kind of behavior of completely positive maps and something very old I recently discovered is Krein-Rootman's theorem, which is an analog of Perron-Frobenius for compact operators. Okay, so now we have this. So these, and now I want to say, okay, if we look at any, say, analytic functions classically on the disk, it has a natural topology on it. What is the topology? Topology of uniform convergence on compacta. This topology can also be given by seminorms of suprema over subdisks. Okay, but now I want to do the same thing. So I want to take my, say, the ring of entires and give it a topology. I'm going to write it as the inverse limit of these H infinity Ds, but for just growing balls. Okay. So, and the result we were able to get, and this is a tricky thing because somehow the local theory is much nicer because Cohn essentially paved the way already for this. He has a lot of results in the sense that, okay, if you have a local subring of the formal power series that satisfies this and that property, then it's automatically a semifield. Okay. But now if you start with the ring of all, and I recall that this is the ring of all NC entires, they're defined everywhere. And in fact, their power series converge on every row ball of radius r that you take. This thing is no longer a local ring. It is a completion of the free algebra with respect to this topology, right? The topology of uniform convergence of subballs. Now, one thing you immediately notice, and I know that people in the audience are very familiar with that, is that, well, there's nothing special about the row ball. You can take any other operator space structure and give the topology that's going to work the same way. But the row ball is special for us because of the technology we employ in the proofs. And that's, for me, it's an interesting question whether this can be simplified or reworked so that it works for other operator space structures. Okay, like you take balls, let's say the polydisk or the non-commutative, I don't know, diamond or whatever, or even other quantizations of the ball. Why so special about the row ball? Okay, for column ball, it's going to be very similar, but they're very much alike in a lot of things. What we were able to prove is, in fact, that this thing is also a semifer. So this is actually a very different proof. And what we had to do is go to the basics, basically, to prove the fact that this is a semisphere using a definition. And basically, so the definition of a semisphere, you can prove that something is a semisphere in the following way. Let me kind of spell it out here on the side. So you have some functions, let's say. Let me write it in blue. So it's kind of, say, f1 to fn and g1 to gn in OD. Okay. What you want to show is that assuming that the sum I goes from 1 to n, fi gi 0, okay, you want to show that there exists a matrix S in GLN of OD, so it's an invertible matrix over OD, such that basically if we take this and call it F, and take this and call it G, then what we have is basically F transpose G, right? If we replace G by SG and F by whatever it should be, right? So I guess S transpose F as inverse transpose F transpose is 0 also. But this is 0 in the trivial way. What does it mean? Cohn says that a ring is a semisphere if every such relation can be trivialized. Namely, you can find an invertible matrix such that you hit your row and column with it in an appropriate way, and the relation becomes trivial because always you have either 0 meeting something here or something here meeting 0. Okay, so basically either fi or gi in the new expression are 0. At least one of them is 0. That's called trivialization of the relation. And if you can trivialize any relation of any length, then it's a semisphere. Now, how would you do that in the entiers? And the trick is to use the inner-outer factorization. So as I said, H infinity D is very much like the H infinity, the classical H infinity. In particular, it has inner-outer factorizations. Even you can take out Blaschke factors if you want. And you can do it also for matrices. And you basically do something like, okay, you take your relation, and you look at a certain ball, and you find an approximate solution. Okay, and then you build the closer solution, then you take the limit, and you show that actually the things that you can trivialize these balls are will give you in the limit something in OD. I can construct, this is kind of a trick that goes back to Arendt's, I believe. He has this paper on different type of relations, but the idea is kind of the same. You construct approximate things that trivialize the relation on a smaller ball, and then you kind of go up and use the fact that a lot of things you can approximate well by these restriction maps. So this is the theorem, but it immediately tells you by Cohn's result that, sorry, before that, that it has a skew field of fractions, right? And by right, the fractions of the entiers should be the meromorphic functions, right? And this is, I think it's, it goes without saying that this should be the non-commutative meromorphic functions. But somehow our technology also allows something a bit more. We can show that every finitely generated right ideal in OD is closed. And this is true for one. If you take so an ideal is closed if and only if it's singly generated in the ring of entire functions in one variable. Here we can only show one direction. So if you have something which is finitely generated, then it's closed. We don't know how to show that if it's closed, then it's finitely generated. I suspect it might not be true, but I don't know. I would hazard the guess that if it's free, it should be closed. And we have some kind of Nullstellensatz type result saying that if we have an ideal generated by some f1 to fm, then we can take its sort of variety. So we look at all the operators and matrices and the vectors such that the vector is orthogonal to the ranges of all your fj, of all the generators when you evaluate them on X. Then we take all the matrices, all the functions in OD such that they are also orthogonal to the same y. So the ranges are orthogonal to the same y's at the same axis. Okay. This is obviously a right ideal because if you multiply here by a function, then let's call it h, say, then it's not going to change anything. And if you take a sum of two such things, it's also not going to change anything. So this is a right ideal. And we can show that actually this is I. Okay, and then the fact is that it's not hard to show that this is the closure of I, okay, because you can basically separate. But to show that this is I precisely requires a bit of playing around with the same techniques I've described previously. Okay. So since it has this universal skew field of fractions, I'll call it OD. Now we can play a game which we couldn't play with the compact realizations, because evaluating compact realizations is a bit tricky. We have some results in this direction recently, but it's much trickier because unlike matrices, once you take a tensor product with compacts, for example, if you are in a von Neumann algebra, like you take a tensor product with B of H, say, that's already, if you were type 2-1, you're no longer type 2-1, you're type 2 infinity, and that's the whole different thing. But here you can just look at these things, right? You can write it. You don't need to write realizations. You do it using just the Cohn theory. Use full matrices, right? So for every f and md, we can, such that it's defined on our semicirculars, we can actually play the same game. So first of all, for every one of our random variables, for n big enough at omega, this is defined, right? So this is in the domain of this function. And the norms converge. What we couldn't show for a very long time, and that somehow the way I wrote it here is not obvious, that you can even ask the question that there are no meromorphic relations for matrices. Like there is no meromorphic entire, like globally defined meromorphic expression, so some rational expression in entires essentially, that is zero or undefined on all matrices. Like this cannot happen. Okay, and we were able to, I would believe so now, and I'm going to say a few words about it in a few slides. We believe that we can show it now, that there are no meromorphic relations for matrices, and therefore for every element of F, you can ask whether it's defined, and these should make sense, okay, once you're there. Okay. So here is a question. Is this the same skew field? Okay. We don't know. Okay. The recent development, like I said, is that there is an embedding. Okay. So it is not hard to see that we said that everything in OD admits a compact quasi-nilpotent realization. So you have an embedding like this. The problem is that unlike in the commutative case, it does not say anything about embeddings of skew fields. Even if you have an embedding of rings, that say semifers or whatever, so that they have universal skew fields of fractions, they don't need to be related. They're universal skew fields of fractions. So how do you prove that there is such an embedding? Well, first of all, I wrote here that the image is dense is because the rational functions are there. And in some sense, everything with the compact realization you can approximate by rational functions well, in some sense. So somehow the image is in some sense dense inside. There's no topology here, but at least if you evaluate, you can approximate it in values by rational functions. So how do you prove that there is such an embedding? So you say that a map of rings is honest if for every n and every a it preserves the inner rank. Okay, so basically, if you have something over R, you have a full matrix, right? Then it cannot become non-full over S. Okay, obviously, not every map is such. Okay, but you can have various weird embeddings where even if they're injective, of course, if the embedding is not injective, you're done. But if you even you have like an injective embedding, right? An injective homomorphism, you might have full matrices that start to split over the bigger ring. Okay. And it's a big theorem of Cohn, the inertia theorem, is that it doesn't happen between, say, for the free algebra, embedding of the free algebra into the formal power series. And it's not an easy proof. It's not very hard, but it really uses all of his theory about the free ideal rings and all this stuff. So proving honest, so it's kind of hard. Recently, so struggling with this for a while. We hope that we were able to show that this embedding is actually honest. And this is a tricky proof because you need to really know what's going on. Because think of this as local, okay, and this is global. So maybe once you restrict to a small neighborhood of zero, your matrices, which didn't factor, suddenly do factor into some row times column. It basically boils down to the question of if you have a full matrix over the entires, can it happen that all it's never, you can evaluate it on any matrix tuple, can it happen that the determinant is always zero? Right? And it's not obvious why it's not happening. It's not even obvious for polynomials, and the proof is not entirely trivial for polynomials and for rational functions. Why doesn't it happen? But there you kind of can play a game with skew fields and so on, and you can show that actually, well, if its determinant vanishes identically on the level, then it's zero, and then you can go to and use some heavy machinery, like there are no polynomial relation satisfied by all matrices, or no rational relation satisfied by all matrices. Okay, that's something this is a theorem you could use to prove this kind of simple looking fact. But here you don't have such theorems, so you need to do something different. And what we did was basically, again, employ a lot of analytic tricks like inner outer factorizations in these subalgebras, and trying to extend them or push them a bit lower. And that's basically kind of the idea of the proof here. Okay. Thank you very much for your attention. So I'll be happy to answer any and all questions.
Thank you very much. Questions, please.
Well, I had a question with the compact realization. And every time when you choose the power series, it looks like ordered, right? You're not choosing like mixed monomials.
Oh, of course,
So,
monomials, no, they are mixed in some sense. What do you mean mixed monomials?
I mean, you're fixing for the Z1, Z2, Z10, like in
Yeah.
one fixed. Right? So,
No, I don't do that. So my
actually, they're
monomials,
not positives, right?
sorry?
Whenever you have these actions of the power series formal as an operators, so this map is not a homomorphism. Am I right?
Which map?
I mean, for example, if you take two power series multiplying in an algebra,
Usually, no. But if your power series converge in some nice way, then yes. You are saying that you want to do something like the hereditary functional calculus, where you choose the order of the stars and well, here I'm assuming that all of them are you can take any word that you want. You don't need to do this. But I usually assume, right, that this power series converges uniformly in terms of its homogeneous components, right? So you can evaluate every homogeneous component. That makes sense, of course. It's a polynomial, right?
okay, yes.
Yes, and that's what
Well,
this
if you,
condition tells you, right?
yeah,
But in
if you take
fact,
the two f and g, multiply them in the formal algebra, and its realization, they're the same, or just so?
sorry,
Do you
no, no,
have
no,
sort
no,
of
no, no, no,
functional
no.
calculus?
You
I don't know.
so okay, so sorry. If you're asking about realizations, then you have an algorithm to write a realization, right? They will have a realization given by basically something upper triangular, right? Um,
Ah,
but they might not be you might not be able to evaluate both of them on the same thing, right? So it's like classically, I mean, you might not so you have the algebra of all these power series with compact realizations, but that's the problem. You cannot really evaluate the entire algebra of things, right? You can take a specific function and evaluate it, okay, and try to evaluate it. Right? And the question is, why does it even make sense? With matrices, it's somehow straightforward. But for operators, it's not as straightforward as that. I mean, but usually the questions, like what happens is that you cannot usually evaluate all of them, right? There's only one, I guess, homomorphism, which is zero, right? Because you can always have things that don't converge on your operator, right? On your tuple of operators. Because you can have compact realizations which have a very big column norm, for example. Right. So then the series will converge on a very small domain. So now the realization makes sense only on a very small ball, right? Even if you kind of write this realization and you try to evaluate it, then okay, it might not make sense, right? It doesn't mean that the function stops at this ball, just like with the classical power series, right? But still, it doesn't. So what happens for rational functions where it's easy, because these are matrices, you can really write this realization always. And you can ask yourself whether it's invertible or not. And the theorem is that, well, if you have your minimal realization, then this pencil that you have that you want to invert in the realization is invertible at your tuple of operators in the stably finite algebra, if and only if the function is defined there. Okay.
mhm.
But for compact realizations, it's a bit trickier because this is not quite unique, and you want to see that this is well defined. And this is why we wanted to understand the other side of things, right? Because these are hard to evaluate, whereas The power series that converge everywhere, well, these are easy to evaluate, right? And then you can try and write rational expressions in them. Okay, these might not make sense, but at least you kind of make the things you write, you build them from do, right?
Okay.
I hope that I
Yeah.
understood your question.
Yeah. One more question concerning operator spaces. You said you want to use operator spaces to define the topology, but you have the contraction condition there, right? You need something special there.
You mean right?
So
Well, there is a paper of Efros and Webster, I think, right?
yes,
Yes, I think so, on local operator spaces. So
yeah,
this
that's
thing
right.
is a local operator space because it's an inverse limit of operator spaces, which you just take, say, the disk algebra, which is the norm closed algebra generated by the left shifts, or okay, you can just view it as functions on the ball of radius r, okay,
Yeah.
with its operator space structure being you look at matrix valued functions and take the sup norm. Okay, so you take the closure of the free algebra under these norms, you get an operator algebra because it trivially satisfies the Blecher-Rowan-Sinclair conditions. And now you take the inverse limit and you get an operator space, local operator space in their sense. That's how they build all of their local operator spaces, right? Like inverse limits of operator spaces.
Yeah, that's right. Oh, okay. Okay, yeah, thank you.
More questions, please. I also have a question about your other possibilities of defining an algebra like your OD. So your algebra is so you said that is an inverse limit of non-commutative disk algebras, right?
Yes.
And so what if we replace non-commutative disk algebras by say by the free product of finitely many copies of the disk algebra? So you take the usual
That's the
commutative.
polydisk. Yeah, that's the
Yeah, as
polydisk
a result, you
algebra.
get something like a free polydisk algebra. So does it make sense to consider it? And if
Yes,
yes,
it
then
does. It does. You'll get the same algebra. You'll get the same topology. But the problem is that I think you'll get the same topology. But the problem is that, as I said, I mean, the reason I'm doing it with the disk algebra is purely technical, right? The reason is that I don't know how to work with the polydisk algebra. That's basically the reason. I know a lot about the ball algebra, and they have this inner outer factorizations, and I can play with them, and I can do things with matrices and stuff. But and I would be happy to know how to do it. You can take any operator space structure on CD, take the ball, take the ball of radius r, and take the completion of the polynomials with respect to the sup norm on this ball. That makes sense. And I'll take these balls to infinity and take the right, I mean, and because all operator space structures are comparable, so you can have a big row ball sitting outside of your ball, so you're bounded there. So this gives you the same topology, right? They're comparable in that sense. So it's gonna, but I don't know how to prove it without using the tricks of the disk algebra, the results. So of course, retroactively, okay, the ring structure is the ring structure, and that's what you have, right? So the semi-theorist kind of doesn't know about topology, doesn't know about the disk algebra. It's just a property of the ring, right? But how to do it without using the disk algebra, I don't know. I would be happy to know. I mean,
thank you. More questions, please.
Well, do you have a property like nuclearity? I mean,
yes. So for the entires, it's nuclear. That's old. I mean, I think it's Taylor's student. I forgot his name now. Joseph Taylor's student. He proved that the entires are nuclear. Yeah. So in Taylor's original paper on this non-commutative functional calculus, he claims that none of them are nuclear, but it's not true. He has a mistake there. And if you take some of the I think if you take, like, he has this polydisk algebras, it says none of them are nuclear, but if you take all the radii except at most one to be infinite, then it is nuclear. And it's very easy to see that in this case it's nuclear, right? You don't need to go into this depth, because kind of, if you take a ball, you take a bigger ball, like much bigger ball, the restriction maps are compact, right? The restriction maps are compact, but if you take a much bigger ball, they're actually trace class. So it's going to be nuclear. But if you take the same algebra of power series with radius of convergence R, let's say, so this is like the analytic functions on a ball, this is no longer nuclear. This is Montel, but it's not nuclear. It's Frege Montel.
Okay. Well,
same reason.
know,
I mean, the kind of the maps are compact, but they are not trace class.
Yeah, that's right. So there is a result if nuclear operator space, I mean local operator space, admits only one quantization.
Yes, it's unique quantization. Yes, it's kind of like simplex in some sense.
Yeah. Yeah. Okay. Okay. Thank you.
More questions, please. Well, if there are no more questions, we thank the speaker again. Thank you, Eli, for the.
Thank you very much for
Thank you very
having me.
much.
Thank you.
Okay, so see you next week. Next week our speaker will be Piotr Ivankov. So he'll tell us something about non-commutative algebraic topology.
Okay.
Thank you very much.
Thank you. Bye-bye.